Welcome back. Next we are going to discuss some more problems. Here is one problem. Use Euclid's algorithm or Euclid's division lemma to find the HCF of 135 and 225. We know that Euclid's division lemma, Euclid's algorithm, or you can call it Euclid's theorem, is used to compute the HCF, that is the highest common factor of any two numbers. Yesterday we have discussed the general form. Okay, we know dividend equals divisor into quotient plus remainder. We know that dividend equals divisor into quotient plus remainder. In general form, we will write it as A equals B into Q plus R. Our question is to find the HCF of 135 and 225. HCF of 135 and 225. How we can do this? Listen carefully. From these two numbers, we will pick the greatest number and we will make it as the dividend and the other number as the divisor. In simple words, we will say we are going to divide these two numbers, taking biggest number as the dividend and smallest number as the divisor. Okay, I am going to divide 225 with 135. How many times? 135 and 225. How many times? Only once. 135, 0, 9, 90. So we'll write it as 225, that is dividend equals divisor into quotient plus remainder. This is the dividend, divisor, quotient and remainder. 225 equals 135 into 1 plus 90. So what's the remainder here? We got the remainder as 90. But as per our theorem or as per Euclid's division lemma, our remainder should be 0. So we have to continue the division until we get the remainder 0. So here R equals 90. That means R not equal to 0. Then what we have to do? We have to continue the division by taking 135 and 90 as the dividend and divisor. We will be taking the divisor and the remainder which we got now, and we will be dividing again using these two, 135 and 90. 135 I am going to divide. We will be taking the biggest number as the dividend and smallest number as the divisor. 135 and 90. Once 90, right? How many? 135 minus 90? 45, right? Here also, what we will write? 135 equals 90 into 1 plus 45. Here also remainder is not equal to 0. R not equal to 0. What we got? R equals 45, which means we have to again do the division by taking 90 and 45. Biggest number among those two is 90 and smallest number is 45. How many times? 2 times 90, 0. My God, we got R equals 0. Here we got R equals 0. That means we have completed the division process. Then how we will write? 90 equals divisor into quotient plus remainder. 90 equals divisor into quotient plus remainder. As per our equation, A equals B into Q plus R. From this, we know that HCF will be HCF of 90 and 45 will be how much? 90 and 45 will be 45. HCF of 90 and 45 will be 45. We know that HCF will be the B term, divisor. A equals B into Q plus R. HCF, when we get R equals 0, then HCF will be the divisor term, B term. A equals BQ plus R. HCF will be the B term, that is 45. This will be the HCF of those two numbers, 90 and 45. So HCF of 90 and 45 is 40. That means HCF of what was our question? 135 and 225 is also equal to 45. Both are same. HCF of 135 and 225 is equal to 45. We started from here and we simplified the whole process and we got it as 45. So we found out the HCF, highest common factor of 135 and 225 is equal to the highest common factor of 90 and 45, which is equal to 45. Is it clear? Listen children, now we are moving on to our next problem. Show that every positive even integer is of the form 2q and every positive odd integer is of the form 2q plus 1, where q is some integer. Okay. Positive even integer and positive odd integer. That means positive even integer means 2, 4, 6, 8, 10. 0, 2, 4, 6, 8, 10 and even integer means 1, 3, 5, 7, etc. Okay. As for Euclid's algorithm, what we know? What is our general form? A equals B into Q plus R. I am going to write that. Solution as per Euclid's division lemma, A equals B into Q plus R. Okay. From this question, we know that B will be 2. That is, A equals BQ plus R. If it is in that form, then B will be 2. B will be 2. B equals 2. B will be 2. And here we also know that 0 less than or equal to R less than B. If B equals 2, then the possible remainders will be, what all are the possible remainders? R will be always less than B. Then the possible remainders will be, here we know that B equals 2, because as per our question, every positive integer is of the form 2q, odd integer 2q plus 1. So B will be 2. So we know 0 less than or equal to R less than B. If B equals 2, then the possible remainders will be 0 and 1, because R is less than B. B is 2, then R will be 0 and 1. Okay, then I am going to substitute this in this equation. Okay, positive odd integers 1, 3, 5. I am going to divide 1 with 2, then it will come 0 times 0, remainder 1. Then again 3 with 2, 1s, 2, remainder 1. 5 also with 2, 2, 4, remainder 1. In this we can write 1 equals 2 into 0 plus 1, 3 equals 2 into 1 plus 1, 5 equals 2 into 2 plus 1. In all these equations, 2 is common. That means 2 and 1 will be varying. 1, 0, 1, 2. That means q term will be varying 2q plus 1. A equals 2q plus 1. Same thing. We can do it in two ways. This is a step-by-step method. And if you are doing some examples, if you are going to sort it out by some examples, you can do it like this. By you doing this, it will be more clear. Concept will be more clear. Okay, listen children. Next problem is, show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. This is same as our previous problem. Here B will be what? B will be 6. Okay, 6 cube plus 1, 6 cube plus 3 and 6 cube plus 5. First you need to understand the question well, then it will be very easy to get the solution. So we have some positive odd integers. 6 cube plus 1, 6 cube plus 3, 6 cube plus 5. Then B will be 6. So I am going to write the solution. As per Euclid's division lemma that we know, what? A equals BQ plus R. Okay, A equals BQ plus R. Let A be any positive integer. Let A be any positive integer. Okay. Here what will be B? B equals, as per the question, B equals 6. Okay. As per this, 0 less than or equal to R less than B. Is it clear? Then, if B equals 6, then what will be the possible reminders? We know that R will be always less than B. Here, as per the question, B equals 6. Then what will be the reminders? Possible reminders? 0, 1, 2, 3, 4 and 5. Because R is less than B. R is less than 6. So, possible reminders are what? Because it is a positive odd integer. Positive odd integer. That means negatives will not come. That's all. Positive integer. Positive odd. Then possible reminders are 0, 1, 2, 3, 4, 5. Very easy. Nothing more to think in that. R is always less than B. We know that B equals 6. Then R will be 0, 1, 2, 3, 4, 5. Okay. Then I am going to substitute the value of R to our first equation. This is our first equation. Direct substitution only. I am going to substitute the values of R to our first equation. Okay. Then, first chance is when R equals 0, A equals 6Q plus 0 equals 6Q. Okay, no doubt. Because B equals 6, then Q, R equals 0, then A equals 6Q. Second case is when R equals 1, then what will be A? A equals 6Q plus 1. No doubt, very easy. Third case, when R equals 2, A equals 6Q plus 2. Okay. Then, when R equals 3, A equals 6Q plus 3. When R equals 4, A equals 6Q plus 4. Okay. When R equals 5, A equals 6Q plus 5. We have done with all the possible reminders 0, 1, 2, 3, 4, 5. But in the question, we are asked to find out, show that any positive odd integer, we need only odd integers. Which are the odd integers? 1, 3 and 5. A equals 6Q plus 1. Yes, that's correct. A equals 6Q plus 3. Very correct. 6Q plus 3 is there. And A equals 6Q plus 5. So, the question is proved. Hence proved. Okay. If they are asking positive even integer, then the question will be what? If they are asking instead of odd, if they are asking even, then the question will be 6Q plus 2 then 6 cube plus 4, right? When r equals 0, it will be 6 cube. When r equals 2, 6 cube plus 2. When r equals 4, it will be 6 cube plus 4. So both the questions you can easily find the solution. Okay, I hope this is clear.